When building a custom home, it's easy to focus entirely on what you can see. We often prioritize the layout of the rooms, the color of the siding, and the perfect slab of granite for the kitchen island. But aesthetic finishes cannot hide the physics of a poorly integrated building. Without proper planning, new homes often suffer from high energy bills, drafts in the hallway, sticky summer humidity, and skin-cracking dryness all winter. These failures usually stem from the traditional checklist approach. A contractor hires a framer, then a plumber, then an electrician, with each trade completing their specific task in a silo, rarely considering how their work impacts the next person's. Building science provides a different framework, treating the structure as a network of interacting parts. This discipline studies how heat, air, and moisture move through materials, requiring every component to be engineered for collective performance. This network relies on four forces: the building envelope, mechanical systems, the external environment, and the occupants. Because these layers are connected, altering one forces a reaction in the others. Managing these interactions eliminates hotspots and humidity issues, regardless of finishes. Consider the physics of a common efficiency upgrade. You decide to seal every crack and crevice in the exterior walls to stop drafts and lower your heating bill. By doing so, you eliminate the natural leaks that used to let the house breathe. Now the structure traps the water vapor from your showers, the fumes from cooking, and VOCs. VOCs, or volatile organic compounds, are the invisible chemicals released by cleaning products and new furniture. To maintain air quality, building science requires pairing that tight envelope with an ERV or HRV. An ERV or HRV is an energy or heat recovery ventilator, a mechanical system that pulls fresh air in and pushes stale air out while capturing the heat so you don't waste energy. A similar ripple effect occurs when you upgrade to high-performance windows and thicker wall insulation to block out the summer heat. A traditional contractor will often look at your square footage and use outdated rules of thumb to install a massive, highly powerful air conditioning unit. This chart shows the failure of that oversized unit. The blue temperature line plummets rapidly, satisfying the thermostat in minutes. But because the cycle is so fast, the green humidity line stays flat and high. This is called short cycling. Short cycling creates a cold, clammy environment. The air temperature is low, but the moisture is never removed, leaving occupants uncomfortable despite new insulation. The engineered solution calculates the exact effect of your insulation to install a precisely calibrated unit. As shown, it runs on a longer cycle, gradually bringing temperature down while pulling the humidity line into the comfort zone. By investing in the outer shell of the house, you reduce the workload required from your mechanical systems. In an integrated system, oversized equipment typically guarantees lower performance and higher operating costs. These interactions even extend to minor electrical decisions, like the installation of trendy recessed lights in a living room ceiling. To install a standard recessed light, an electrician must cut a 5-inch hole directly through the drywall and the protective thermal boundary that separates your living space from the attic. If you install 20 of these, you have created a massive pathway for expensive, conditioned air to flow upward, while raw, 100-degree attic heat pours downward into your house. A systems-based builder anticipates this. They utilize airtight electrical fixtures rated for direct contact with insulation and seal the edges from the attic side to maintain the integrity of the thermal barrier. This minor aesthetic choice directly dictates how hard your air conditioner has to work all summer. It proves that no single trade can operate independently without impacting the entire building's efficiency. When you engineer these connections correctly, the physics of the house begin to work for you. An integrated approach delivers 4 specific outcomes: structural durability by managing moisture, improved air quality through filtered ventilation, consistent temperatures across every floor, and significantly lower energy consumption. To achieve these results, you have to shift your hierarchical criteria. You are no longer looking for a project manager. You are interviewing for a systems engineer. Start by asking potential builders about their philosophy on integrated systems. If their focus remains strictly on square footage costs and finishes, they are likely overlooking the underlying building science. Next, ask for their specific tactical air sealing strategies. A qualified builder will be able to name the exact tapes, gaskets, and sealants they use to maintain the building's thermal boundary. Finally, ask if they use a manual J load calculation to size the HVAC equipment. A manual J is an engineering formula that uses your home's specific insulation levels and window types to determine the exact mechanical capacity required. Mastering the invisible physics inside the walls ensures the building envelope and mechanical systems work in harmony. This technical precision creates a structure that maintains its value while keeping monthly operating costs at a minimum for decades.